Hey everyone, today we're going to be talking about the composition of functions. To get the main concept down, imagine that I have four functions going on. I have f1, f2, f3, and f4. Now suppose that I input a blue circle into f1 and it gives me an orange circle. What I'm going to do is take that orange circle and feed it into f2 to get a purple triangle. I'll feed this into f3 to get a green oval, and I'll feed this into f4 to get a white A. So what I've done is at each step I've taken the output of one function and treated it as input for a new function. Looking at this whole collective process, this chain of functions took as input the blue square and outputted the white A. This is the idea of function compositions, where you're essentially combining multiple functions into one. In this process, sometimes you will mash all of these functions together to get a new formula at the very end, or you'll just keep feeding inputs, get outputs, and keep refeeding those into the new functions to see what you get. But let's be more precise. The actual definition of a function composition is the nesting of two or more functions, which will result in a new function. So suppose that I have the two functions f of x and g of x, and I want to study the composition of these functions. So there are two possibilities here. I can get f composed with g of x, which looks like f of g of x, or I could look at g composed with f of x, which looks like g of f of x. Basically, it's like we're evaluating functions at functions instead of at points. So at this point, we're learning just a new definition, but we're not going to be learning too much new math. It's essentially just going to be a lot of algebra. Notice that the little circle here is the symbol that we use denoting composition. And in general, the quantities on the left and right here are not equal. Let's go ahead and jump into some examples. Let f of x equal to x squared plus 2, and let g of x equal to 2x minus 1. And then we'll compute the following. First, we'll compute the function that describes f composed with g of x. So by definition, we'll be finding f evaluated at the function g of x. So what this means is I'll look at f of x, and everywhere I see an x, I will replace it with the symbol g of x. That looks like this, quantity g of x squared plus 2. The best thing to do here is every time you're seeing an x, you should replace it with g of x in parentheses, because that will make the algebra much easier to handle. But now that I have this expression, I can go ahead and replace g of x with this definition, which is 2x minus 1. In so doing, before I simplify, I get the quantity 2x minus 1 squared plus 2. And now, all that's left to do is simplify. So I'll FOIL the expression out and get 4x squared minus 4x plus 1 plus 2, which then simplifies to 4x squared minus 4x plus 3, which is by definition f composed with g of x, and we're done. Continuing along in this fashion, we will compute g composed with f of x, and by definition, that looks like g evaluated at f of x. So just like before, we will look to our g of x, and everywhere we see the letter x, we will replace it with the definition of f of x. Before simplifying, this will look like 2 times quantity f of x minus 1, and then when we replace f of x with its actual formula, we get 2 times the quantity x squared plus 2 minus 1, which will then simplify to 2x plus 4 minus 1, which simplifies finally to the answer, which is 2x squared plus 3, which is g composed with f of x. So this example demonstrates how f composed with g of x and g composed with f of x don't have to be the same thing. In general, they are definitely not going to be equal. One way you can think about function composition is just it's a way of letting multiple functions interact with one another. Sort of like how adding or multiplying numbers will give us a new number in return, composing functions with one another gives us a new function in return. Overall, this is just a new operation that we can do with functions. In this next slide, we're going to take the exact same two functions, f of x is x squared plus 2 and g of x is 2x minus 1, and we're going to start evaluating these compositions at different points. For good measure, I'll go ahead and put up the formula that we computed up here to the right. Before I get started, there are basically two ways of evaluating compositions of functions at a number. You can compute the formula of the composition and then plug those numbers into the new formula, or you can do this sort of ad hoc process that I'm about to demonstrate. By definition, I'm going to write out the composition of f composed with g of 2 as f of g of 2. So think about the first slide where I was giving one function the square to output the circle, which then was fed into the next function, which outputted the triangle, and so on and so forth. The 2 kind of acts as our blue square here. I'm going to feed 2 into g, see which number I get, and then I'm going to feed that number back into f to get our final answer. When you're doing function compositions, you're basically starting at the number that you're evaluating at and work your way outside. So since I'm computing f of g of 2, off to the side here, I'm going to figure out what g of 2 has to be. By definition, g of 2 equals 2 times 2 minus 1, which comes out to 3. So I will replace f of g of 2 with f of 3. And now I can evaluate f at the point 3, which gives me 3 squared plus 2 equals 11. Again, I calculated g of 2, figured out what the output was, and then fed that output back into f to get the answer of 11. But also notice that with the formula I have for f composed with g of x, if I feed 2 into that formula, which was our original input, I still get an answer of 11. So these two things agree, which means that you get the same answer no matter what. It's really just up to you what you want to do. For our next example, I will compute g composed with f of negative 1, which by definition is g of f of negative 1. So like I did above, I'm going to compute f of negative 1 off to the side. In so doing, I get an answer of 3, so I will feed this output of 3 back into g, and I find that g evaluated at 3 comes out to give me an answer of 5. But again, just for good measure, the formula for g composed with f of x came out to be 2x squared plus 3, and when I evaluate that function at negative 1, again my original input, I still get an answer of 5. In this next series of examples, I'll let f of x equal to 1 over 1 plus x, g of x equal to 1 plus the square root of x, and h of x equal to quantity x plus 1 squared. The first thing that I'll do with these is compute f composed with g of x, and I just want the formula for that. So, moving forward, I get f of g of x by definition, which looks like 1 over 1 plus the quantity g of x, and then replacing g of x with this definition, I get 1 over 1 plus the quantity 1 plus the square root of x, which after a round of simplification, I get 1 over 2 plus the square root of x. Now that I have a formula, I can go ahead and start evaluating this composition at points. So let's compute f composed with g of 4. Plugging in 4 everywhere I see an x, I get 1 over 2 plus the square root of 4, which will simplify down to 1 over 2 plus 2, which is equal to 1/4, and we're done. Lastly, we'll compute f composed with g of 3, which will look like 1 over 2 plus the square root of 3. So, when I rationalize the denominator, I end up with a final answer of 2 minus the square root of 3. Using the same functions as the previous slide, I will compute h composed with g of x, and then I will evaluate it at other points. So by definition, I get h of g of x, which looks like the quantity g of x plus 1 squared, which looks like 1 plus square root of x plus 1 squared, which comes out to 2 plus the square root of x squared. And I won't simplify any further because this is enough. Now I'll go ahead and start computing h of g of x at points. First, I'll evaluate h composed with g of 9. So all I need to do is start plugging in a 9 and then simplifying. When I work through the algebra, I end up with a final answer of 25. And for our last example, I'll compute h of g evaluated at 5. Since I can't take the square root of 5 and get a nice whole number, I'll just simplify this down to get 9 plus 4 times the square root of 5, and we're done. So like I said a while back, taking function compositions isn't necessarily new math, it's just using a lot of different algebra to simplify formulas and to evaluate functions, or new functions rather, at points. For our last example, we'll do something a little different. Instead of being given formulas for our functions, we'll be given a graph, and then we'll be asked to evaluate function compositions at numbers. The first thing we'll compute is f composed with g evaluated at 2, which comes out to being f of g of 2. Even though we don't have a formula, we can trace this on the graph. First, I want to compute g of 2, and to do that, I find the 2 on the number line, and then find where the g function sends that value of 2. In our case, by following the orange line, we get an answer of -1, so now we'll be computing f of -1. And then following -1 on the number line and tracing it up to the blue curve, which is f of x, we find we get a final answer of 1. And then for our last example of the day, we'll compute g of f of -2. To do this, we'll find out what f of -2 is by again looking at the x-axis, following -2 up to f of x, which gives us +1, and then we'll evaluate g of +1, which as we trace down, we find leads us to -1. Therefore, g composed with f at -2 is equal to -1, and we're done.